Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basics, Sign of Trigonometric Functions, Concept number 13, Quadrant 2 and Trigonometric Functions. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is super effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a brand new paradigm. I want to include everyone who needs a boost in Algebra 2, and if I could stick every math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose of Algebra 2. You have lots of peers, classmates, and colleagues who could really benefit from this cram session as well. Tell them to inbox me at memedicine@gmail.com so that they too can order the complete Algebra 2 cram session. You'll be glad you spread the word because they'll make great study buddies. And last but not least, the concept of cramming often has a negative connotation, but what people are actually thinking of is hurrying, and that's a result of fear and can consequently be destructive to your learning process. We're not hurrying here, we're cramming. There's a difference. Hurrying is jam-packing tons and tons of unorganized information into your mental, spiritual DNA over a tiny amount of elapsed time, whereas cramming is taking quantum leaps in your understanding in an organized way in what seems to have been an instant. So let's delve into concept number 13, Quadrant 2 and Trigonometric Functions. Quadrant 2 and Trigonometric Signs. Express the trigonometric functions of an angle theta in quadrant 2 as a function of its reference angle, 𝜃𝑟𝑒𝑓. Here's just an example theta, in case you're wondering what theta is referring to. It's referring to an angle, and theta sub ref is short for reference angle, okay? And in a brief moment, you'll understand why we're in quadrant 1 as opposed to quadrant 2. So definitely press pause, and I'll give you a moment to think. And remember, when I say trigonometric functions, I mean the three basic functions and their cofunctions, such as sine and its cofunction cosecant, the basic function cosine theta and its cofunction secant theta, and the basic function tangent theta and its derived cofunction, the cotangent theta, okay? All right, so I hope you came up with your answer by now. And if you didn't, press pause before we continue. And if you don't feel like waiting, let's just delve into this together, okay? Whatever you prefer. All right, so the signs of trigonometric values depend on the sign of x and y in the quadrant in which the terminal side of the reference angle is found, okay? And before expressing the trigonometric functions in quadrant 2, we need to understand the concept of standard position, and doing this will simplify finding all the trigonometric values and their associated signs, okay? An angle in standard position in quadrant 1, that's the caveat, standard position is in quadrant 1. It has 6 key features. That's why I started out in quadrant 1 as opposed to a theta in quadrant 2, okay? The first feature is that its vertex is at the origin. The ray on the positive x-axis, as slightly indicated here, is the initial side ray. And the other ray terminates in quadrant 1, that's called the terminal side ray, okay? So the extent of our angle theta in quadrant 1 in standard position goes to the terminal side ray, terminating in quadrant 1. We'll call this ray R for short, and notice that this angle is acute. So standard position angles are acute because they terminate between the quadrantal angles 0 degrees and 90 degrees. Quadrantal angles being angles whose terminal side rays land on either the x-axis, such as 0 degrees, or the y-axis, such as 90 degrees. Okay, you can even extend this to 180 degrees, 270 degrees, 360 degrees, negative 90 degrees, negative 180 degrees, negative 270, etc. Okay, and notice positive angles enlarge in the counterclockwise direction, whereas negative angles enlarge in the clockwise direction. So it's kind of like backwards according to our like normal standard of thinking. Normally you would think clockwise positive, counterclockwise negative, but the associations are opposite, okay? Those were sides. Okay. So let's highlight the fourth feature of our angle and standard position. Let's say instead of having a terminal side ray, we elect to make the terminal side ray R a terminal side segment by cutting it off here at point P, whose coordinates are x and y, x being the x coordinate and y being the y coordinate respectively, okay? And so the horizontal extent of the ray is going to wind up here at x, which corresponds to the x coordinate, and it rises to the level of y, corresponding to its y coordinate. And notice that the signs of x and y can either be positive or negative. For x, it's going to be positive in quadrants 1 and 4, but negative in quadrants 2 and 3. And for our case, in this session, it's going to be negative because we're interested in quadrant 2. Same for y, it's going to be positive in quadrant 1 and quadrant 2. If for our case here, it's going to be positive because we're interested in quadrant 2, but y is going to be negative in quadrants 3 and 4 because it corresponds to the negative y-axis, okay? All right, so that's just something to definitely keep in your mind. And the sixth feature of this whole standard position concept is that the ray, or it looks like now what can be a hypotenuse. It's a segment length. It's no longer a ray because we cut it off here at point P. So it's bound by point P and the vertex, which is the coordinate points 0, 0. Those are really convenient points, okay? And so because it's a segment length, it's going to be the length of a hypotenuse of what seems to be a right triangle. So we'll just indicate our right triangle here, our imaginary right triangle that is, because resolution of this segment length, which was formerly a ray, is going to give you the extent of the x coordinate, the extent of the y, and what you have is a right triangle. And this is the basis for finding the trigonometric functions in a Cartesian coordinate plane, okay? Yeah, so let's continue. And like I said, R is going to be a segment length, so it's never going to be negative. That's because you're always going to square the x coordinate and square the y coordinate, okay? And because the initial point is 0, we don't have to indicate that. So this is actually a play on the distance formula, and you square both coordinates, take the sum, and then undo squaring by taking the square root. Okay, so this will always be a positive measurement. So we can look at this as the hypotenuse, and these three bad boys are the basis for finding all our trigonometric functions, as well as the angle theta. This is our angle in standard position, specifically our positive acute angle in standard position, positive because we're traveling or we're getting large in the counterclockwise direction, okay? But hey, we're not interested in quadrant 1. Rather, we're interested in quadrant 2. And as an aside, the reference angle for quadrant 1 is just going to be theta itself. That's pretty easy. That's pretty self-explanatory. So obviously the reference angle is the positive acute angle made with the x-axis here. But we're not going to have this convenience as we go to quadrants 2, 3, and 4, specifically here quadrant 2. So let's solve this issue, or resolve this issue rather. So let's say we're interested in quadrant 2, okay? And let's say that this is our theta. It's an obtuse angle rather than a small, not small, an acute angle in quadrant 1. So we're going to demonstrate what this reference angle would be. Basically, here goes our hypotenuse, and the reference angle is going to be the negative acute angle made with the x-axis. We just basically took everything that we showed you previously over here, and we did a vertical flip about the y-axis. We cut off our ray, and we turned it into a ray segment, and we resolve our ray into its x and y components. And notice now that because we did a horizontal flip, the x component is, the x coordinate rather, is negative. You know, if we had our p right here, this is negative. Y is still positive. We're still in the realm of the positive y coordinate, but we're on the negative aspect of the x coordinate, okay? So this is the major difference, and this is what's going to affect the trigonometric signs in quadrant 2. And now our theta reference is no longer equal to theta, rather its theta reference is equal to the extent of quadrant 2, so the quadrantal angle 180 degrees minus theta. And that makes sense, okay? So theta reference here is going to be the negative acute angle made with the x-axis. Negative because in order for the terminal side to terminate, you have to enlarge in the clockwise direction going this way, okay? All the arrows are drawn this way. You can look at this as a negative angle. All right, and again, let's say you have your reference angle, but you want to figure out theta. Theta is equal to 180 degrees, the extent of quadrant 2, the quadrantal angle bounding quadrant 2, minus the reference angle, okay? But with all this said, we're still not interested in this. We just basically want to know the 6 primary trigonometric functions, which don't include the inverse functions, because inverse functions are going to give you an answer of the angle of interest. We're not interested in that just yet. If you want to know about that, go to some other Cram sessions and order the complete session by inboxing me at memedicine@gmail.com. Okay. So obviously here in quadrant 2, only the sign of, we have x, but it's really the sign of theta is going to be positive. And I'll show you just why just in a minute. So let's say we have the sine of theta that's going to be equal to the side opposite the reference angle divided by the hypotenuse, okay? And again, y wasn't affected. We're still in the positive y realm. So you're going to have the side opposite theta reference, which corresponds to the y coordinate, divided by the hypotenuse or ray segment length, which is always positive, as I demonstrated earlier. And so the cofunction of the sine of theta is going to be the reciprocal of this. The numerator now being the segment length, or the hypotenuse, divided by the side opposing the angle, which corresponds to the y coordinate. But now things get shaken up a bit because we want to find out the cosine of theta as a function of its reference angle, and that's going to be the negative cosine of the reference angle, all because well, this negative comes from the fact that the reference angle is enlarging in the negative direction, and the actual answer is going to be negative x coordinate divided by the ray segment length. because in general trig, we know that the cosine of this particular reference angle is going to be the adjacent side, which corresponds to the x coordinate, which is now in the realm of negative x. Okay, that's where this negative comes from, divided by the hypotenuse length. And so the cofunction, which is just a reciprocal of the cosine of 𝜃𝑟𝑒𝑓, you can pretend that this is 𝜃𝑟𝑒𝑓 here, is going to be the hypotenuse segment length divided by negative x. I really should have had the secant of 𝜃𝑟𝑒𝑓, but you get the point. So the secant of 𝜃𝑟𝑒𝑓, you could say the negative, let me just write it in so I don't confuse you. This is going to be the negative secant of 𝜃𝑟𝑒𝑓. And we would want like this, we would say the secant of this theta is equivalent to the negative secant of its reference angle, which is going to yield the hypotenuse segment length over negative x, okay? And last but not least, our derived quotient trig function, the tangent of this particular theta in quadrant 2 is going to be the negative tangent of theta reference, okay? Again, the negative here comes from the fact that this angle is growing in the negative clockwise direction, and the negative in the actual numerical value will come from the fact that you're now on the negative aspect, located in the negative aspect of the x. How do you say this? The x-axis, rather than the positive aspect of the x-axis, okay? So you're going to have our tangent, which is basically the side opposite the reference angle, which corresponds to the y coordinate, divided by the side adjacent to the reference angle, which corresponds to our negative x coordinate, okay? And last but not least, the cofunction, which would be the cotangent of this particular obtuse angle theta in quadrant 2, would be equivalent to the negative cotangent of its reference angle. Let me just draw that out for you. The negative cotangent of 𝜃𝑟𝑒𝑓. Sorry for this janky. I promise, like, give me a month and I'm gonna get a really good writing system so that this can flow smoothly and eliminate lag time, okay? So the negative cotangent of 𝜃𝑟𝑒𝑓 is going to be equal to basically the reciprocal of the tangent, which is going to be the negative x coordinate divided by the y coordinate, or the adjacent side divided by the side opposing the theta reference angle, okay? So as you can see, we have our basic trig functions here and their associated signs, whether the signs are positive or sometimes negative, specifically for quadrant 2. Intellectual comprehension of this material was not difficult, and after the short amount of time it takes to complete the entire Algebra 2 cram session, you'll be prepared to answer a battery of questions about all the Algebra 2 concepts. So inbox me at memedicine@gmail.com to order the complete cram session. Thanks.